Okay, now that we've got a general overview of weather in the past couple of weeks, we're going to focus just on the atmosphere, its origins, its composition, and structure. So we're looking at a broad picture of the atmosphere today, and basically looking at maybe how we observe it a little bit. So with that, let's see what we can move on here to the next one. So what is the composition and structure? Uh, there are interesting things about the weather that you can get an impact in one part of the world that impacts another part of the world. For example, there's dust in the atmosphere. One of the interesting things, especially towards the summertime, is that dust can be transported all the way from the Sahara Desert to South America or even into southeastern United States. There were cases actually early last summer where visibilities in Miami went down to 1 mile in dust because of dust from the Saharas. So you've got to remember when you're looking at weather that everything over the whole world is each area can impact another area as we go through this. And dust is one of the things that is in the air. It can actually cause damage to coral reefs in the Caribbean and all. So weather can go from nice and beautiful to miserable very quickly. And in the atmosphere right now, if you look at it, there's an atmosphere. The Earth system contains an atmosphere, a hydrosphere, which is just water, the geosphere, which is more rocks and mountains and topography, and then the biosphere, which is the plants and animals and us. And you look at the atmosphere, it's relatively thin. It really, half of its mass is within 18,000 feet of the Earth's surface. So if you went up to Mount Everest and went up to the top of Mount Everest, you would be above half the atmosphere. So 99% of the atmosphere is actually below 20 miles. Think about it. If you ran a marathon, you would be running over the length of the atmosphere. So that is not a real far distance. The atmosphere goes up into space. So we talk about the homosphere being the lower part of the atmosphere, basically within atmosphere can stretch out for a long way. So there is that area that we call the homosphere has 78% nitrogen. And another part of it is 20%, almost 21% oxygen. If you're at the Earth's surface and the atmosphere is exactly that composition, if you went up to the top of Mount Everest, the atmosphere would still be that composition. It's just that there's a lot less atmosphere there for you to have. That's why breathing and all becomes very difficult as the higher up you go. So you can see here the amount of oxygen and nitrogen in the current atmosphere. Another part is there are liquid and solid particles. And maybe that dust we talked about coming from Africa. The volcano that erupted out of Tonga the other day. Water vapor. It can actually contain up to 4% of the lowest 1 kilometer of the atmosphere. It could be water vapor, causing clouds, precipitation. We need carbon dioxide for life, for photosynthesis with plants that we eat and all. So, and both of them impact how radiation is dealt with, whether we get warmer or colder in the lower part of the atmosphere, depending on that. Pollution. When I was growing up back in the 1960s, there were smog almost every day in Los Angeles. There were parts of London, England, that you could get visibilities down to 100 feet just from smog, which was just a mixture of fog and pollution. We've cleaned up our act a lot since then. We're going to talk about the scientific method just shortly here. What happens in the scientific method, and I'm going to give you a case that deals with the Appalachian Mountains. Say I observe thunderstorms coming into West Virginia. Those thunderstorms continue moving, and sometimes they dissipate on the east side of the Appalachian Mountains, and sometimes they come across in their full strength. So, as a meteorologist or as a forecaster of the weather, I want to know why. What times am I going to have that thunderstorm move across, and what times am I not? Actually, we worked with with North Carolina State University on this project. We formed the hypothesis that it might have something to do with stability, or how unstable or stable the atmosphere is. We'll talk more about that later. So we tested that. We ran computer models. We looked at observing what had happened in the past and what the stability was. We actually were able eventually to come up with a certain parameter that, yes, if this parameter was met, we could expect these thunderstorms to continue moving east of the mountains and maintain or even strengthen. And if that parameter was not met, most of the times the thunderstorms would die. So this is how you go about looking at the scientific method, and what we're going to talk about throughout this whole course is using this method. There are atmospheric models such as chambers that can look at tornadoes, numerical models. I've worked at those when I was in college. I used them when I was a forecaster. I helped way back when, helped develop some. But all models have errors. We cannot solve the equations correctly. They're just impossible mathematically to solve that relate to weather. So they're all approximations. That's why numerical weather forecasting, no matter how good it's gotten, it still has errors in it. Observing the atmosphere. ASOS is one of the best observing systems in the world. It's automated, and it can take a complete observation that is needed for any aircraft to land at that airport. That's why ASOSs are at almost every single airport in the United States and around the world. Many of them are. And they actually report data every minute so that there's a continuous feed of information there that you can actually watch how the clouds would change during the last 5 minutes even, or maybe how the temperature is moving. These are wonderful systems for trying to learn what's going on at that location. Remember, I'm talking about a specific location at an airport. Then there are also cooperative networks. These are volunteers that actually record daily temperatures, max and min, and precipitation. That data is available daily, once a day, usually at 7 a.m. in the morning. And some of it, maybe we ask them to get a little bit more information. Sometimes the Weather Service might call and ask for the data a little sooner than maybe they would want to give it to us. But it's great for looking at long-term climate or agricultural needs. You can actually tell droughts from this kind of information from rainfall, filling in the gaps. Where ASOS is at an airport, this might be in somebody's backyard 50 miles from that airport. We don't have that information, so here we do now. Then there are volunteers, COCORAs. It's a great volunteer network. It measures all kinds of precipitation, rain, snow, hail, and it does it in real time. So that if I wanted to know, hey, how much rain's falling out of that area right over downtown Beckley, maybe there's a COCORAs right there. Instead of blowing at the airport where there's an ASOS in Beckley, maybe I wanted to know what downtown Beckley. It isn't that far, but there could be, in the summertime, for example, with thunderstorms, a big difference. Radiosondes are a way to look at the upper atmosphere. They're just a balloon that's launched that's carrying an instrument. And that instrument looks like these, the radiosonde replacement program. They go up and they record temperatures, they record moisture, they get wind direction, and they record pressure as it's changing, as it's going up in the atmosphere. All this information, and the radiosonde is going upwards here. Dropsondes, on the other hand, come out of an aircraft. They're really used by a lot of hurricane hunters, but every once in a while in the winter, there are actually aircraft that go out and sample winter storms. They also can use dropsondes, and these go down. Remote sensing such as radar and satellite that we've used all throughout. And here is just a temperature profile. Notice that in the troposphere, the temperature drops typically on the average. Then it begins to warm again when you get to the stratosphere. The mesosphere, it cools off, and then the thermosphere begins to warm up again. Auroras are just simply from the solar wind interacting with our magnetic field. They can be beautiful things that can occur over the poles mainly. And here you can see the stronger the solar wind, the stronger further out the aurora might go. So let's just take a quick peek at just a couple things here. Here's a surface front, and it's yesterday, on Thursday. Here is the cold front, and I mean it is a cold front. Temperatures are in the upper 40s and 50s east of it. Behind it, they're in the mid-30s. Oh yeah, the rain actually starts after the front moves through. So ahead of the front, cloudy, but much warmer. Behind the front, temperatures are cooling off. Interesting question. If I was you, where, if I was driving Interstate 64 goes like this towards Beckley, where along Interstate 64 would I cross that boundary? I might be interested in that, especially if I'm driving and want to know where I'm going to hit the rain or whatever. So that is an issue that always is occurring in weather. We just don't know exactly locations of where these fronts are. We can approximate them, and we're pretty good at it, but we're not perfect. So that's why sometimes where we think the front may have passed a location, we like to know. We try to get reports about it or whatever to try to find. Meteorologists are hogs for information, for data. We love it. The more data we can get, the better we can analyze things. The better we can analyze things, the better the forecast is going to be. So this was a day ago. If you move one day into the future, which brings you to today, that front is way down into the Florida, and you can see clearly there's plenty of cold air coming in right now with big high pressure. One of the other interesting things, looking at this, fronts are three-dimensional. I've talked about that before, and observing them, we want to know what a radiosonde might look like. So this was this morning out of Wallops. If I was looking at this, this is just temperature plotted and dew point, which is just a measure of moisture. So the closer the dew point is to the temperature, the more moist the air is. Well, look at the winds here. They're out of the north right through about 850 millibars, 5,000 feet up. But really, there's a whole other front very low down here. That's the Arctic air. There's actually two fronts here. There's one Arctic cold front, which is really, really cold. And then there's another cold front through here. And if you wanted to know where the stratosphere was, look at the temperature starting to warm up right here. This is where the stratosphere is. If I looked at the same thing up further to the northwest, up to Pittsburgh maybe, you can see the cold air much deeper. And the stratosphere, a little harder to find really, maybe really low, actually right about here because of the cold air. So observing the weather, we look at it every day. We want to look at it from satellite. We want to look at it from radar. We want to look at it from observations like ASOS, whatever. But that's what we're trying to show with this today. Just trying to get a complete picture and understanding of what the weather's actually doing.